Okay, so as I mentioned, as you saw when we went through the syllabus, our first unit is on whole numbers. Well, not whole numbers, but integers and real numbers. Now, the difference between whole numbers and integers is integers doesn't include negatives. So we're going to be dealing with them. But this first unit, and actually technically the first 3 units, are going to be a lot of material that you've seen before. So I try not to cover it in the same way that you probably would have seen it before. I mean, if that method worked with you, you would know it and you wouldn't really need to go through it again. And going through it again the same way if you didn't understand it is kind of a waste of time. So I take a little bit different approach. My approach to basic math is, rather than explaining how, I want to explain why. And from the why, we can figure out how to do things. The main reason I do that is I've found through the years, first of all, most of the struggles students have when we get into the more difficult topics come from the fact that they really don't understand the simplest topics. They memorized how to do it, but they didn't know why. And without that knowledge, knowing how to adjust that to do the more complicated problems is difficult to do. And I've also found that most students really do not understand some of the simplest concepts in math. Like I said, they've memorized them, but they don't understand them. Right down to what is probably the most basic concept in math, which is a number. What is a number? Well, if I put 4 up here, show of hands, how many of you would tell me that that's a number? Most of you would, right? Some of you got that look on your face like you know there's something coming here. 4 is a numeral. It is just an amount. Now you might be thinking, well, isn't that what a number is an amount? Well, a number technically has 2 parts to it. It does have that amount, telling us how much, but it also has to tell us of what. So we might have 4 cows. Now that is a number. Every number has 2 parts to it. The first part tells us how much, and I'm going to call that part the count. That's the amount. And the second part tells us basically of what. What do we have 4 of? In this case, it's cows. And I'm going to call that part the name. Okay, you call it the label, the units, depending on what you're doing. It has different titles. But we're just going to give it the generic term, the name. Now, this is not my way of forcing you to have to label everything. On a test or whatever, I'm not going to take off points if you put down 17 and don't put 17 inches. Now, that's not my purpose. The involvement of that name or that label is actually vital in understanding how operations work. So with that in mind, let's take a look at our 2 most basic math operations. The 2 most basic operations in math are addition and multiplication. Some of you might be wondering, where did subtraction and division go? Well, subtraction is really part of addition. They're not really 2 operations. They're the same operation. Addition is going forward, subtraction is going in reverse. So any rules or concepts that apply to addition also apply to subtraction. The same is true with division. Division is really part of multiplication. Multiplication is going forward, division is going back in reverse. They're actually what we call inverses of each other. One operation reverses the other. If you add 4 to something, if you come back and subtract 4, you get back to where you started. If you multiply a number by 7, and you take that answer and divide it by 7, you get back to where you started. So they're the same operation, just one is forward and one is reverse. So now let's take a look at addition in terms of numbers using both a count and a name. So I'm going to start out with 4 inches plus 7 inches. What do we get for a result there? 11 what? Inches. So let's take a look at what happened here with our 2 parts. So we've got the 4 and the 7 are our two counts. We combine those to make 11. We're adding here, so we combine those counts with addition. So we combine the counts. If we look at the names, however, we had inches and inches, and we ended up with inches. When we add numbers, we keep the same name. Adding inches to inches, we still have inches when we're done. Now you might be looking at that thinking, that's not really groundbreaking information. But there's a difference when we look at multiplication. If I have 4 inches, and I'm just going to abbreviate it as IN, times 7 inches. First of all, is everybody familiar with that dot for multiplication? It means the same thing as the x. It's just the algebraic way of writing it. So 4 inches times 7 inches, what do I get? I get 28, but not inches. Inches squared, or square inches. If you think about it, if I'm multiplying inches times inches, generally what I'm doing is I'm looking at an area. 4 inches by 7 inches, I'm getting inches squared. So what's going on here with my counts again, I have 4 and 7 still. This time I was multiplying, so I combined them with multiplication. So I still combine the counts. The difference here is the names. I had inches and inches, and I ended up with inches squared, or square inches. When I multiply numbers, I also combine the names. So looking at that, you might not think that that's worth your money for the class quite yet. But there's an important, that distinction is very important. Almost everything we do in operations and math with our different forms of numbers follow those two rules, come from those two rules. In fact, these two rules define what numbers we can even use in each operation. For example here, for addition, let's say I have 3 cows plus 5 boys. Do I get 8 cowboys? No, of course not, right? Or if I did it the other way, 5 boys plus 3 cows. Do I get 8 boy cows? No. Anybody with a farming background in here? So you can tell me that is a whole bunch of bull, right? Okay, I know, a long way to go for a joke, but there's a point behind it. Being a math teacher, I'm required to have a really stupid sense of humor, by the way, so you get used to it. But the point behind this is when I add numbers, I'm going to keep the same name, which implies I had to start with the same name. I could combine 4 inches with 7 inches by addition because they had the same name. So when we add or subtract, we must have the same name. I can't add 3 cows with 5 boys because they have different names. Just like if I had measurements, like 7 feet plus 2 pounds. When I add 7 feet and 2 pounds, I'm going to get 7 feet and 2 pounds. They have different names. I can't combine them. Now, there will be times where we can change the name. I might have 2 feet plus 7 inches. Well, I can change that name so that I can combine them if I want to. 2 feet can become 24 inches. So now it's 24 inches plus 7 inches is 31 inches. So there will be times where I can change one of the names. I can convert one of them so that I can combine them. We'll see that a lot in fractions. Now, we could not add 7 feet plus 2 pounds. But if we were trying to multiply 7 feet times 2 pounds, when I multiply, I'm going to combine the names. which means I don't have to start with the same name. When I multiply, I combine the counts. What's 7 times 2? 14. But I'm also going to combine the names. Feet times pounds are foot-pounds, which is in physics is a unit of torque, or a unit of moment if you're looking at structural analysis and stuff. That is a valid unit. We can multiply or divide things that have different names. So that concept there explains a lot of what we've been taught as special rules for other forms of numbers. For example, everybody's favorite type of number, a fraction, 3/7. I know, I saw that look. If I asked people on the way in the door what they hate most about math, 4 out of 5 people would say fractions. The other one would usually say the teacher. Just not yet, thanks. They give me a 1-day grace period. The top number of fraction is referred to as the numerator. The bottom number is the denominator. Good. A little side note here. I am a horrible speller. You saw me pause halfway through the word there. That's because I got partway through it and I forgot how to spell it. I also realize I do have sloppy handwriting. If anything ever appears up here that you can't read, I assure you it was intended to be in English. Just don't be afraid to ask me what something says. I will not be offended. So looking at these, the numerator. What does it mean to numerate? Well, every 10 years, our government sends out people to do the census, to numerate the population. What are they doing? They're counting. That is a count. To denominate means to classify or to put into groups. Like we have different denominations of money. We have different denominations of organizations. To denominate, like I said, means to classify or to give a name. Title, label, same type of thing. Yep. So a fraction, 3/7. A lot of people look at it and they see 3 numbers. But it really is just like 4 cows or 4 inches. It is a single number with 2 parts. Each number has a count. The count is 4 for each of those, 3 for this one. And a name. We have cows, we have inches, and we have sevenths. So here, 3/7 means we have 3 of something, and what it is sevenths that we have. So when we add with fractions, come on, there we go. We might have 3/7 plus 2/7. Now, somewhere around 3rd or 4th grade when you learned how to add fractions, that teacher told us that in order to add or subtract fractions, you must have a common denominator. Yes. That was not a separate rule for fractions. Nothing new. Anytime we go to add numbers or subtract numbers, we must have the same name. Common denominators is just making sure we had the same name. And then that same 3rd grade teacher told us that when you add fractions, you combine the numerators and you keep the common denominator. So adding the numerators, 3 plus 2 is 5, and keeping the common denominator, again, it's not a new process for fractions. That's how we add any number. We combine the counts, and we keep the same name. It's the same process. If I wanted to add something like 2/3 plus 1/5, can I add those the way they're written? Yeah, right now they have different names, so we have to change them. Just like we did with the 2 feet, we changed it to 24 inches to give it the same name. When we do fractions, we'll look at renaming those to give them the same name so we can add them. But for now, all we need to know is that we can't add or subtract them unless they have that same denominator or same name. When we multiply fractions, if I had 3/7 times 2/7, That same 3rd or 4th grade teacher taught us when you multiply fractions, you just multiply straight across, right? 3 times 2 is 6. 7 times 7 is 49. Well, again, that's nothing new for fractions. When we multiply any number, you combine the counts. 3 times 2 is 6. Then you also combine the names. 7 times 7 is 49. If I look at my 2/3 and I try to multiply it by the 1/5, I don't need the same denominator. I do not need a common denominator to multiply. Because with any form of number, I do not need the same name to multiply. I'm simply going to combine the counts. 2 times 1 is 2. And then also combine the names. 3 times 5 is 15. So all of those special rules we were taught for fractions are not special rules. They are the same rules that apply to all other forms of numbers. They just look different with fractions. Next, let's look at something like 0.21, a decimal. Now, I said 0.21, but the formal way of pronouncing that would be 21 what? Hundredths. There we go. And when you write it out like that, it's relatively easy to see the count. We have 21 of something, and the name is the hundredths. So if I wanted to add 0.21 plus 0.3, adding always works best for me if I set it up vertically, so let's do that. Is that going to work? What did I do wrong there when I set that up? What do I have to do? You have to line up the decimal point. Probably about that same 3rd or 4th grade teacher told us, when you add decimals, you have to line up the decimal points. Well, why? Okay, yeah. It has to do with the names. This is 21 hundredths here. This is 3 tenths. They have different names. So really what we're doing to give them the same name is we're adding a 0 there. So it's 30 hundredths instead of 3 tenths. So when we do that, then the decimal points automatically line up. When we add them, 21 and 30 make 51. Where does the decimal point go? Straight down. Perfect. When we bring that decimal point straight down, what we're doing is keeping the same name. 21 hundredths plus 30 hundredths better be 51 hundredths. When we add or subtract, we keep the same name. If I wanted to multiply 0.21 times 0.3, do I have to worry about lining up the decimal point? No, we don't. No. Because when we multiply, we do not need the same name. So 21 times 3 is 63. Where does my decimal point go?
3 spaces.
3 spaces. I have to put a 0 in here and then put my decimal point, right? Where'd you get the 3 spaces?
Count the spaces behind the decimal point.
Perfect. Somewhere along that line, that 3rd or 4th grade teacher told us, when you multiply decimals, you count 1, 2, 3 decimal places in the problem. So then you have to count back 1, 2, 3 decimal places in the answer. But why? Well, the teacher told me so, right? Well, this is 21 hundredths. This is 3 tenths. When you multiply, you do combine the counts. 21 times 3 is 63. But then you also combine the names. Hundredths times tenths is thousandths. So when you're counting those decimal places and putting that many decimal places in your answer, all you're really doing is combining the names. So all of these special rules that you were taught for fractions and decimals and other sorts of numbers are not special rules. They're just the process of following, bless you, of following those basic rules for addition, subtraction, multiplication, and division. They just look different with the different forms of numbers. In fact, while we're at it, let's throw in algebraic numbers quick. A lot of people freeze up here when we mix letters with our numbers, but 4x is just an algebraic number. It has a count of 4 and a name of x. It behaves exactly the same way as 4 inches or 4 cows or even 4 sevenths. The difference is we're more comfortable with these because we know what an inch is and we know what a cow is and we know what a seventh is. We don't necessarily know what x is, but it doesn't matter. If I have 4x plus 7x, I'm going to get 11x. I combine the counts I'm adding, so I add 4 and 7 makes 11. And when I add or subtract, I keep the same name. But if I wanted to do 5x plus 2y, what do I get? I get 5x plus 2y. Yeah, just like feet and pounds. I can't combine them with addition or subtraction, at least, because they don't have the same name. If we were multiplying, let's add 4x times 7x, what do we get? 4 times 7 is 28. We combine the counts. We're multiplying, so we combine them with multiplication. But also combine the names. X times x is x squared. Just like inches times inches. Oops, a little bit more. Inches times inches became inches squared. X times x becomes x squared. What about that 5x and 2y? What if I had 5x times 2y? Perfect. I combine the counts. 5 times 2 is 10. And then I also combine the names. Just like feet times pounds became foot pounds, x times y becomes xy. Now we're going to go over all those rules in more detail when we look at each different type of number later on in the course. But for right now, I wanted you to see this big picture up front, how you can see that all of the different processes we are going to do come back to just a very, very few basic rules. And I'll try to link things back to that as much as I can as we go through the summer. So let's look at, okay, so we've seen these basic rules, but how does that tie into the larger numbers that we're used to working with? Well, the concept that kind of ties all this together is the concept of place value. Place value is another one of those very simple concepts that is often misunderstood, or at the very least its huge importance is not really grasped when you're going through it. So if we start at the end of the number, at the decimal point, and we work our way backwards here. What is this last place value right here called? That's called the ones place. The next one? Tens. And then? Hundreds. And those are actually our 3 place values. And they are repeated over and over again. So ones, tens, hundreds. Ones, tens, hundreds, and so on. Now this first group here is called a base group. So it is just the ones, tens, and hundreds. This next group is called the thousands group. And then we have the millions group. And then the billions and the trillions and so on. When we name a place value, we name its place value and its group. So this is just the tens place. This is the 10,000s place. The 10 millions place. Now I'm not going to go over how to pronounce a number. Hopefully we don't have to go back quite that far in our thing. But it is very important to look at something like 4,275 here and see what it really means. what we are used to seeing as numbers is an abbreviation. 4,275 really is 4 1,000s and 2 hundreds and 7 tens and 5 ones. Some textbooks refer to this as expanded form of a number. What it really is the full form of a number. And what you can see when a number is written in this form is that every digit of that number has a count and a name. This is 2 hundreds. This isn't just a 7, it's 7 tens. So in just a second, when we look at our basic operations, that's going to come into play. One of the other things that these place values are important for is rounding. If I give you 4,275 and I ask you to round to the nearest 1,000. To the nearest 1,000 or nearest 1,000 would mean the same thing. Now, most of us know how to round. How would you go about doing it? Well, first you identify the number that's in the thousands place. What digit is in the thousands place here? 4. That's the thousands place. So rounding to the nearest 1,000 means we are going to cut it off after that digit. Technically, rounding to the nearest 1,000 is referring to a number line. And what it's saying is if we have a number line where we only look at the thousands, pretend those are evenly spaced. And if I put 4,275 on there, which would be right here, which one is it physically closest to? The 4,000. Yeah. So 4,000 is the nearest 1,000. That's what nearest 1,000 means, physically nearest or closest. Well, without having to draw out a number line, the way we figure it out is just like we did here. We identified the thousands digit. Then we look at that next digit. That being a 2 tells us we'd have 1, 2, 3, 4, 5, whatever. The 2 is obviously closest to the lower one, so we go down to 4,000. If it was one of these larger numbers, we would go up to 5,000. So that would be the 6, 7, 8, 9, right? Well, the question is, what if it's right in the middle? What if that were 4,523? Well, here's our thousands digit, the 4. We look at that next digit, it's a 5. And 5 would be right in the middle. But does that number end at 5? No. There's stuff after it. So that it is past the midpoint. It does go up to the next larger one. So when we see a 5 in that next digit, we round up. The only time that is an issue is if it happened to be exactly 4,500 and we're asked to round to the nearest 1,000. Then it really is exactly in the middle. Well, what have we been taught to do with that? Still round it up, right? If that next digit's a 5, we round it up no matter what. Because most of the time there's going to be other digits after it that put us past the halfway point. So our convention is we usually round them up. Now, with that said, if some of you are going into machining or CNC or mechanical design or something like that, into some sort of an engineering-based field, there are times where they round 5s down. We're not going to get into that because that's a specialized rounding process. It's something called rounding to the evens. If it's something you're extremely curious about, let me know and I will show you. But I don't want to do it in class because I don't want to confuse you. Because for our purposes, when that next digit is a 5, we are going to always round up like you've been taught. So anyway, by the way, since we got number lines up here, another interesting fact about a number line is this. One of the things that we get done in... stray marks. One of the things that we do in math that confuses people all the time is this. Fill the box with equals, less than, greater than, so on, right? What this is really asking, here's the 8, right? And the 3 is somewhere here. What direction do we have to go? Or the 8 is on what side of the 3? That side. Notice that's where the greater than symbol came from, is that arrow at the end of the number line. So if you're having problems, I know we've all been taught things like the alligator eats the larger number, stuff like that. But that's where that symbol actually comes from. Okay, let's look at our basic operations with whole numbers here quick. If I wanted to add something like 426 plus 251. Now I am going to write these out in full form. So this is 400s and 2 10s and 6 1s. This is 200s and 5 10s and 1 1. When we were taught how to add and to subtract numbers, for that matter, we were taught you had to be very careful and line up the columns. Well, the reason being, as we mentioned before, each digit has a count, but also a name. This is not just 2, it's 2 10s. So I can only combine it with other 10s. So by lining up the columns, I'm making sure I line up the things that have the same name. Once I've done that, then I can just add down the columns. 400s and 200s make 600s. 2 10s and 5 10s make 7 10s. And 6 1s and 1 1 make 7 1s. So I get 677. Now, some of you may have watched what I just did there in adding those and noticed I did something unusual. Can anybody tell me what it was? I started on the left and I went to the right. How do we normally add numbers? Yeah, you start on the right side and you work your way back to the left. You start at the smallest place value and work your way back to the left. Why do we do that? There you go. Yeah, in case you have to carry. If I have a number like 379 plus 258. I start on the right side and work my way back to the left because I have this. 9 plus 8 is 17. Well, I can't have 2 digits in that spot. So I'll keep the 7 1s and I'll carry the 110. Perfect. 1 and 7 makes 8 plus 5 is 13. So what do I do again? Leave the 3 and carry the 1. Perfect. 1 and 3 is 4 plus 2, 6. So it's 637. That process of carrying is actually a relatively new process, less than a couple hundred years old. Before the carrying became popular, one of the ways that this could have been done. Now, don't put this part in your notes, because I'm not going to try to change the way you add numbers. I'm just throwing in a little bit of math history here, and there's a point behind it. But one of the ways that this could have been done is just this. 3 plus 2 is 5. 7 plus 5 is 12, so 2 drop the 1. 9 plus 8 is 17, so 7 drop the 1. I got to the same answer. Very different than what you're used to doing, isn't it? But mathematically, it's all equivalent. It doesn't matter whether I carry that up here to the top and bring it down, or if I just slide it over. I'm accomplishing the same purpose. The reason I show you this is I'm not trying to change how you add numbers, by no means. But we've all been told this myth that in math there's only one way to do it correctly. And that's not true. I could show you 4 or 5 different ways to add numbers that will work every time and give you a correct answer that look very different. So there isn't just one way of doing it. There is one basic set of concepts behind it, and those set of concepts can be applied in different ways to get you to the right answer. Now, I'm a realist, and I realize that you all have calculators, or you will have them soon, and you're not going to, especially 3 digits, and if you got up to 4 digits especially, you're not going to do it, write it out by hand and work with the numbers by hand. You're probably going to punch them in a calculator. And I don't have a problem with that, but I call it intelligent or thoughtful calculator use. When I look at this, 379, I'm thinking that's about 400. 258, I'm thinking that's around 300. 4 and 3 makes 700. So when I punch this in the calculator, I better get an answer close to 700. Because it's very easy to do something like this. So 379 plus 258 is 4,037, right? What did I do wrong? I hit the 7 twice. It's easy, especially if you got these fat fingers like I do. I got sausage fingers here. Very easy to hit an extra button on that calculator and not realize it if you're not paying attention. Or I might do get 407. Well, what happened there? Yeah, the 5 didn't register here when I tried to enter it. And that happens a lot with your calculators. The buttons get a little sticky and you have to press them really hard, or you think you pressed it and it didn't register. Well, if I didn't have this estimate in my head, either one of those answers, I might have written it down and just gone on with life and used it for something else and been wrong. So make sure you are doing that thought, looking at it, thinking about where do I expect this answer to be before I punch it in my calculator. So you know, you won't catch every mistake, but you'll catch some of the worst ones. Now for subtraction, I'm not going to bother doing them out in long form like that because I think you get the point. When you add or subtract, we have to line up the columns because of the names. So this one's already lined up, so I'm going to go ahead and subtract. 8 minus 5 is 3. 3 minus 2 is 1. 4 minus 1 is 3, so I get 213. Now, did anybody catch what I did there again? I went backwards again. I went left to right. It worked here because I didn't need to. Now in subtraction, it's not carrying its borrowing, right? But most of the time, we'll run into problems like this. We start on the right and work our way back to the left because 6 minus 7 can't be done. So what do we have to do? Borrow from the 3, that'll become a 2, and this becomes a 16. 16 minus 7 is 9. 2 minus 9 can't be done. So what do we have to do? Borrow from the 9, that'll be an 8, and this is now a 12. 12 minus 9? 3. 8 minus 2? 6. We have 639. Now, just like with addition, that borrowing process is relatively new. One of the ways that this would have been done before might have looked like this. 9 minus 2 is 7. 3 minus 9 can't be done, so we're going to borrow from this. That's a 6. This is 13. 13 minus 9 is 4. 6 minus 7 can't be done, so we take from the 4, that's a 3. This is 16. 16 minus 7 is 9. Notice I got to the same answer. It's just a little bit different way of doing it. Again, I don't expect to change how you subtract numbers. I just want to make you aware that there are different ways of doing it. Now, again, I don't expect you're going to do a lot. The calculator's there, you're going to use it, right? I mean, it's nice if you know how to do it by hand. To let you know about my background, I came from engineering, and several of the last jobs I had were structural engineering on construction job sites. It wasn't uncommon for me to have my calculator dropped in the sand and a couple buttons don't work, or set in the windshield of the truck and you come back and it's like all wrinkled in the sun. I've had a lot of days where my calculator wasn't available and I had to do stuff by hand. So it is nice to have that ability. But I also understand that many of you are going to go to the calculator. Nowadays you have cell phones, so you almost always have a calculator available to you in some form anyway. But still, I would look at this and say 936, that's about 900. 297, that's about 300. 9 minus 3 is 6, that's about 600. So again, have that estimate in your head before you punch buttons in the calculator. Okay, so then, next we're on to multiplication and division. I could have something like 32 times 21. And now this one I am going to do in expanded form, long form. So 32 is 3 tens and 2 ones. 21 is 2 tens and 1 1. When we multiply or divide, we do not need the same name. So what that means here is these 2 ones not only can be combined with the 1 1, but they can be combined with the 2 tens. In fact, every digit of one number can be combined with every digit of the other number. Our process of long multiplication is nothing more than an organized way of doing just that, making sure that every digit of one number gets combined with every digit of the other number. The variations of long multiplication are simply varying where we start. What most of us have been taught is you start with the bottom number and the last digit, right? So we start with 1 1. Now we're going to use that with every digit of the top number. So 1 1 times 2 ones. Well, combining counts. 1 times 2 is 2. But we also have to combine the names. Ones times ones is just ones. Anything times 1 is itself, right? Then we move to the next digit of the top number. So we're still using the 1 1 times the 3 tens. Combining counts. 1 times 3 is 3. Combining names. Ones times tens is tens. Now when we multiply, you were taught, when you move over to this next digit, what do you have to do down here? Okay. Either put in a 0 or move over a space. The reason for that 0 is going to become apparent here in just a second. So now we do move over to the 2 tens. What's 2 tens times 2 ones? Well, 2 times 2 is 4. Tens times ones is tens. Putting in that 0 or leaving a blank space there is just making sure our tens stay lined up with our tens. Now we have our 2 tens times our 3 tens. What's 2 times 3? 6. And then multiplying our names, tens times tens, is hundreds, yes. So now then we can combine the ones with the same name. We got 2 ones. Oops. 3 and 4 make 7, not 6. 7 tens and 600. 672. Now again, I realize especially with multiplication, you're probably not going to do a lot of longhand multiplication. You're most likely going to look at this and say, hey, that's about 30. This is about 20. 3 times 2 is 6. Now remember, when we multiply, we combine the names. So tens times tens is hundreds. The shortcut, by the way, for that is when you multiply, you just combine zeros. You got 1, 2 zeros in my problem, 2 zeros in the answer. Just like counting the decimal places, you had 1, 2, 3 decimal places in the problem. You do the same with the zeros. Long division is going to take a little bit of background here, because long division is the one operation that has been mutilated the most from what it really is. So I'm going to do just a little bit of background before we do long division. And to do that, I'm going to step back just a touch to multiplication again. When we first started learning how to multiply, usually right around first grade, before you memorized your multiplication tables, before you knew that 5 times 3 was 15, how did you figure it out? Yeah, 5 plus 5 plus 5. That was taken as 5 3 times, right? So you added 3 5s together, giving us 15. The definition, or one of the definitions of multiplication, is just repeated addition. Now, we said that division follows the same rules as multiplication, only in reverse. So if I look at 24 divided by 8, I said that multiplication is repeated addition. Can division be thought of as repeated subtraction? Well, 24 minus 8 is 16, that's once. 16 minus 8 is 8, that's twice. 8 minus 8 is 0, that's 3 times. 24 divided by 8 is 3, because I can subtract 8 from 24 3 times. In fact, our remainder system comes from that. The stray marks are killing me today. I might have like 23 divided by 5. Well, I do 23 minus 5 is 18, that's once. 18 minus 5, 13, that's twice. 13 minus 5, 8, that's 3 times. 8 minus 5, 3, that's 4 times. Can I take 5 away again? No. So 23 divided by 5 is 4 with a remainder of 3. Now there are different things we can do with that remainder. We can make it a fraction or a decimal, or we'll look at those as the summer goes on. But that's where the remainder comes from. 23 divided by 5 is 4 with a remainder of 3, because we can subtract 5 from 23 4 times with 3 left over. So now with that said, let's take 49,273 divided by 21. Now we just said that division is repeated subtraction. I am not about to start subtracting 21 from 49,000. We don't have that kind of spare time, right? But let's think about this for a second. If I had just 57 divided by 2, I'm kind of in the same thing. I don't want to start subtracting 2 from 57. But what I could do is start subtracting big bundles of 2. Like 2 times 10 would be 20, right? I could subtract 20 from 57 twice. But what I did was I subtracted 2 in a bundle of 10. So subtracting 20 was 10 of those 2's. And I did it twice, so that's 20. Now I still have the 17 left over, so I can start subtracting the individual 2's. Let me get back down to this one, and it might make a little more sense. Now again, I don't expect you to change how you do long division. So this next little process you don't have to put in your notes if you don't want to. But the full process of long division does look like this. I want to start subtracting 22 in big bundles. To figure out how big of a bundle to use, I use the place values of the number I am dividing. So what's the place value of this first digit? 1, that's the 10,000s. So I'm going to do 21 times 10,000. That's 210,000. Can I subtract that from 49,000? No, that's too big, isn't it? So we move to the next place value, the 1,000s. 21 times 1,000 is 21,000. Can I subtract that? Yeah, in fact, I can subtract it twice, right? 21,000 times 2 is 42,000. $3,727. So I have 7,273 left. But what I really subtracted there was I subtracted 2 bundles of 1,021s. 1,000 times 2 is 2,000. I just subtracted 21 2,000 times. Does that make sense? So my next place value is the hundreds. 21 times 100 is 2,100. Can I subtract that from the 7,000? You bet. In fact, sorry, I got to get used to the delay on the network. It's longer than it used to be now with the new system. So I'm sorry I keep cutting you guys off on the other sites. I'm going to try to pause a little bit longer for you. In fact, I can subtract it 3 times. 2,100 times 3 is 6,300. There's 3, 7, and 9. 973 left. Well, how many times did I just subtract that 21? 3 times 100. I just subtracted the 21 300 times. What's my next place value? Tens. 21 times 10 is 210. Can I take that from what's left? You bet. How many times? 4. 210 times 4 is 840. I can take that away. Got 132 left. Well, how many times did I just take the 21 out? 4 times 10, 40. And now, of course, all I'm left with is the 21 itself, or 21 times 1. I can take that out. Looks like 6 times, 126. Leaves me with 7. So I just took it out 6 more times, with the remainder of 7. So 21 goes into 49,273. 2,346 times. 2,346 times, with a remainder of 7. That's the full process of long division. Now, I'm willing to guess that none of you have ever seen that whole thing. Yeah, a lot of shortcuts in there. You might be thinking, that looks nothing like what I was taught. But it really is. It's exactly what you were taught. We were just taught a lot of shortcuts. What we were taught is this. 21 does not go into 4, so we leave that blank above the 4. That's exactly what we did here. We tried 21 10,000 times. It was too big. So we moved over to the next digit. 21 goes into 49 twice. 2 times 21 is 42. We subtract it to get 7. That's exactly what we did over here. 21,000 goes into it twice. So we got 42,000. That's 2,000 times. We subtract. Notice that's exactly what we did here. We just left out all the zeros. We would bring down the next digit, the 2. 21 goes into 72. 3 times, that's 63. Again, notice it's just leaving off the zeros here. That's all we're doing. So we'll get the exact same answer. Now again, I also realize that the calculator is going to come into play. Long division is the one operation I try to avoid doing if I can. So you're looking at this thinking, okay, that's about 50,000 divided by about 20. We're looking at a little under 2,000, 2,500 is what we're hoping for that to be. Which is about what we got. Now some of you might go, how do I know how to estimate that? Well, the last thing I want to do is stand up here and preach to you how to estimate. Because Estimation only works if it works for you. What I mean by that is everybody could look at this and have a different way of estimating. Some people might look at this and say, I'm going to round that to 48 so it divides by 2, so I know it's going to be about 2,400. That's just fine. Others might look at this and say, okay, 5 doesn't divide by 2, so I'm going to divide 50 by 2 to get 25. Then I cancel out a 0, so I got 2 zeros on the end. It's 2,500. Whatever works for you for estimating is the right way to estimate for you. With that said, my math lab does ask you to do some estimating, so that's one where you may have to look at the example to do it. On a test, I will never ask you to estimate, because to me, estimating is a personal thing. It's whatever method makes sense to you, because estimating is only helpful if you actually do it. So me forcing you to do it my way, you're going to do it when I'm forcing you to, but then you're not going to do it when you don't have to. Come up with a method that works for you, that's quick and easy, so that you will actually do it before you punch numbers in the calculator. Okay, our next step then is we're going to move into negative numbers. Everything we've talked about so far is what you would call whole numbers. Whole numbers are your counting numbers plus 0. So it's 0, 1, 2, 3, 4, on, all the way on up to infinitely large. What we're getting into now is something called integers. Integers include the whole numbers, zero, 1, 2, 3, and so on, but they also include the negatives. So negative 1, negative 2, negative 3, and on down the line. So to understand these, there's two things we're going to understand, we need to talk about. One is we need to talk about graphical representation of numbers. So if I have the number, or actually the numeral I should say, 6, there's a couple of different ways I can represent that graphically on a number line. One is I can just put a dot at 6. Well, if I'm just trying to represent the value, that's the most efficient way to do it. But if I'm going to use it in an operation, it doesn't help us perform, it doesn't help us do anything. So another way to represent it would be like this. Start out at 0 and make an arrow to 6. That is called a vector. And a vector is just a really fancy word for an arrow that starts at 0 and goes to that number. If I wanted to represent a negative 6, well, that'd be an arrow that started at 0 and went the opposite direction, back to negative 6. Notice, though, there's two things about these vectors that come into play. The direction, they're pointing in opposite directions. One's positive, one's negative. And then another fancy word for a simple concept called magnitude. Magnitude is just the length. What can I say about the magnitude of those two vectors? Same magnitude, just different direction, right? If I take this one, I should be able to slide it. They should lie on top of each other. If I'd drawn my stuff to scale, and it would. But it's not going to, because I didn't. There's a reason I'm a math teacher, not an art teacher, by the way. But it just seems it came out pretty close there. Same magnitude, just opposite direction. One's positive, one's negative. When we add numbers, adding numerals, I should say, because the numbers would include the name. When we add numerals, we are using these vectors. So let's say I have 5 plus 3. There's my vector for 5. There's my vector for 3. I take that addition means physically combining the vectors. So I'm going to take the two vectors. Come on now. And I'll put them end to end. And we notice what I get is one big long vector that is 8 units long. It goes up to 8. 5 plus 3 equals 8. That shouldn't surprise anybody, right? So when I'm dealing with integers or possible negative numbers, if I had 5 plus a negative 3, I'm going to put it in parentheses just to separate it so you know that's a negative and nothing else. I have my 5. Here's my negative 3. When I go to put those together, I take the negative 3. Come on. I put it over there with a 5, and I notice I end up at 2. Perfect. Now, I don't expect you to draw out a number line every time we work with integers. But I actually do keep that picture in my head. Like if I have something like 12 plus a negative 7, here's what I'm thinking. Here's 0. 12 is positive. It goes that way. Negative 7 goes the opposite direction and has a smaller magnitude, so it's shorter. So it stops somewhere in there. So that picture tells me, first of all, my answer is positive because I end up on the positive side of 0. And the arrows, the vectors, go in opposite directions. So the result is the difference in their magnitude. What's the difference between 12 and 7? 5. So that result is positive 5. If I have 12 plus a negative 15, the picture is going to be similar. Here's 0. 12 goes that way, positive. Negative 15 goes the opposite direction, but this time it's longer, so it goes past 0. So that's telling me that I end up on the negative side of 0. The vectors go opposite direction, so it's still the difference in magnitude. Difference between 12 and 15 is 3, so it's a negative 3. I might have a negative 8 plus 5. So here's 0. Negative 8 goes this way. Positive 5 goes the opposite direction. Longer or shorter? Shorter. So it stops, again, still on the negative side. They're opposite directions, so it's the difference in magnitude. So the difference between 8 and 5 is 3, so negative 3. Or I might have negative 10 plus 19. Those zeros here. Negative 10 goes this way. Positive 19 goes the opposite direction, and it's longer. So I end up on the positive side. And again, they're opposite direction, so it's the difference in magnitude. Difference between 10 and 19 is 9. It's a positive 9. I might have a negative 7 plus negative 11. So now again, here's 0. Negative 7 goes this direction. Negative 11 goes the same direction. So that picture is telling me I'm obviously on the negative side of 0. The arrows go the same direction, so I add the magnitudes. 7 and 11 makes 18, so my result is negative 18. You look confused there. He's thinking multiplication and division. Yeah. Yep, exactly. When you multiply and divide, you get two negatives make a positive. You think about it this way: if your checkbook is in the red, your checkbook's at negative $120, and you lose $20 more, you've gone further back. So two negatives still stays in the negative. So addition with integers can be thought of like that. Well, the next step is subtraction. A lot of us have developed a lot of really bad habits with subtraction through the years. And by no fault of our own, because that's what we were taught to do. If I give you 8 minus 3, the picture that most of you would draw on the number line would look like this. Start at 0, you go to 8, then you go back 3, and you end up at 5. 8 minus 3 is 5. Again, hopefully no big surprise to anyone. But as I look at this picture, that picture looks an awful lot like 8 plus a negative 3, doesn't it? Because it is. Subtraction is not an operation on its own. Division isn't either, by the way. That's why at the beginning of class I said the two basic math operations are addition and multiplication, because subtraction and division are not their own operation. They are part of addition and multiplication. This symbol that we know as the subtraction symbol means add the opposite. It's just a shortcut. Subtraction, any operation always actually acts upon the number that follows it. So here that subtraction, the minus, goes with the 3 that comes after it. What this is really telling us to do is to take 8, subtracting 3 means add the opposite of 3. What's the opposite of 3? Negative 3. So 8 minus 3 is really 8 plus a negative 3. Now, realistically, all of us have been doing subtraction since kindergarten. We know that 8 minus 3 equals 5. So I'm not going to make you change that one. If you look at that and that makes sense, wonderful. I'm not going to force you to change your thought process. But where it gets confusing is when we have something like this. Negative 7 minus 5. A lot of people look at that and say, well, it's negative 2, isn't it? Well, here, remember, this is negative 7. The color didn't change for me. Negative 7 plus the opposite of 5 is negative 5. So there's negative 7 and another negative 5. That result is actually negative 12. Or we might have the one that's the more confusing one, looks like this. 8 minus a negative 2. Now, does the 8 change? No, the subtraction always acts on the number after it. So this is 8 plus, what's the opposite of negative 2? Positive 2. Good. Subtracting a negative is the same as plus a positive. So 8 minus a negative 2 is 8 plus 2, or 10. You don't need to draw out the picture for that one. Or you might have negative 5 minus negative 13. Again, that one's going to become what? Perfect. Negative 5 doesn't change. Subtraction becomes plus the opposite. The opposite of negative 13 is positive 13. So we've got negative 5. Positive 13 goes the opposite direction, and it's longer, so we end up on the positive side. So it's a positive. Arrow, the vectors go opposite direction, so it's the difference in magnitude. Difference between 5 and 13 is 8, so it's a positive 8. That one right there, subtracting with negatives, is one that we will revisit several times throughout the summer. And it's one that I'd say 3/4 of my students struggle with. Yes?
Well, in high school we taught subtraction and maybe numbers and teaching work.
Sure. Yeah. And that's one of the shortcuts out there that does the same thing. If that works for you, please keep using it. Most of the calculators you have will have a very simple to use negative button as well. So please double check your work using the calculator to see if it's coming out with the same answer you do. Because like I said, that is one, subtracting a negative or subtracting with negatives, with integers in general, is one that will be the result of a lot of mistakes when we get into the algebra portion of the course. So make sure that's something you're working with. We will keep going over it over and over again. But if you're struggling with it, don't get frustrated, because I guarantee you 3/4 of the class is struggling with it. Multiplication. We said that 5 times 3 is 5 plus 5 plus 5. It's repeated addition. That's just saying take 5 3 times. So with that in mind, negative 5 times 3 would just be perfect. Negative 5 plus negative 5 plus negative 5, which would be negative 15, which fits in with what most of you have been taught. A negative times a positive has to be a negative, right? We also might have 5 times a negative 3. Now, we don't have to have the multiplication symbol in there. We could just do 5 and negative 3 in parentheses, and it's implied that that's multiplied. Can I take 5 and add it together and negative 3 times? Now, that doesn't make any sense, does it? But multiplication is what we call commutative. As long as all we're doing is multiplying, we can switch the order. So I can make that negative 3 times 5. And now that's saying add the negative 3 together, 5 times. So negative 3 plus negative 3 plus negative 3 plus negative 3 plus negative 3 is again negative 15. Again, fits with what we've been taught. We've been taught a positive times a negative is also a negative. How about negative 5 times negative 3? What's the answer to that one? Positive 15. Good. At some point, we've all been told a negative times a negative is a positive. So the question becomes, why? They said so, right? Well, we can't take negative 5 and add it together negative 3 times. We can't switch it either. We can't take negative 3 and add it together negative 5 times. That doesn't work either. The definition of multiplication breaks down here. It doesn't work. It doesn't apply to this problem. And that actually happens in math quite often. And when we run into a problem like that where the basic definition does not work, where it fails or breaks down, we look for a pattern. We look at numbers where it does work, and we see if we can continue that pattern to get to where we want to be. So for example, if I have negative 5 times 3, we already said that that's negative 15, right? So let's keep the negative 5 and change what we're going to multiply by. So we're going to negative 5 times 2, which is negative 10. Negative 5 times 1 is negative 5. Let's look for a pattern here. We're starting with negative 5 every time. What are we doing to the number we multiply by? We're reducing it by 1. Right? Yeah, we went from 3 to 2 and 2 to 1. What happens to our result each time? It goes up by 5. Went from negative 15 up to negative 10. From negative 10 up to negative 5. So let's check and see if that pattern continues. So I start with a negative 5. What would I have to multiply by? 0, because I'm reducing that by 1 again. My result is 0. Perfect. 0. Did that increase by 5? Yes, it did. My pattern continues. So, if I take negative 5 times a negative 1, I reduce that by 1 again. My answer has to go up by 5. That'd be positive 5. Negative 5 times negative 2. I reduce that by 1 again. My result has to go up by 5. It'd be 10. Negative 5 times negative 3. Again, I reduced it by 1. The result has to be 15. Has to go up by 5. So when you multiply a negative times a negative, you get a positive. And the reason is because it completes a pattern. Division is the same way. Let's say we have 18 divided by a negative 3. Well, first of all, is this going to be positive or negative? Negative. A positive divided by a negative is a negative. What's 18 divided by 3? 6, right? If I have a negative 21 divided by 7, first, is the answer positive or negative? Negative. Negative divided by a positive is also a negative. In other words, if there's one negative and one positive, it's also a negative, right? 21 divided by 7? 3, so it's a negative 3. What if I have a negative 20 divided by a negative 4? Positive or negative? Positive. Two negatives. A negative divided by another negative is a positive. And 20 divided by 4 is 5. So positive 5. The way to double check division, by the way. The definition of division. 8 divided by 2 equals 4. Because if I work backwards, 4 times 2 equals 8. So here, does negative 6 times a negative 3 equal a positive 18? Yeah, negative times a negative equals a positive. Negative 3 times a positive 7, does that equal a negative 21? Yeah, negative times a positive equals a negative. Positive 5 times negative 4, does that equal negative 20? Yes, positive times a negative does equal a negative. Okay, our last step. We've got 10 minutes left, so one more topic to cover for our first day. I know I'm looking out there and I'm seeing full written across everybody's forehead, but one more thing we have to do. We've covered all of our basic operations. And there is one more actually out there that we didn't cover that I'm going to just make a quick mention before I do this last topic. What's that symbol mean? Yes, squared. 7 squared. That's 7 times 7, which is 49. Technically, that's 7 to the power of 2, and a power is repeated multiplication. So what we're going to be looking at here for the last 8 or 9 minutes is problems like this. Where I have more than one operation to do. Now, some people might look at this and say, well, I read going left to right. I'm just going to do that left to right. 9 minus 3 is 6. 6 times 5 is 30. 30 plus 4 is 34. Which makes sense, but it is wrong. In order to make sure two people look at a problem like that and get the same answer, we've defined something called the order of operations. Most people incorrectly view the order of operations as a set of steps. It's not. What it really is levels of priority. Kind of like at work, if your supervisor tells you something and then a person above them on the chain tells you something, who do you listen to? The one higher up, right? That's the one you have to deal with first. The person higher up the food chain, right? Same type of thing with order of operations. The higher on the level of priority, that's what has to happen first. Our highest level of priority is enclosing symbols. Now, many of you have probably been given just parentheses as that one. Parentheses is one type of enclosing symbol, but there are several others. And parentheses, even though they're there, are not always an enclosing symbol. Sometimes, like here, that wasn't an enclosing symbol. That's just telling us that's a -4 instead of -4. Our second level of priority is exponents. Exponents include two things. The power, like we just saw, the 7 squared, 7 to the power of 2, and roots, which we haven't really talked about yet, but those both are part of exponents. Our third level of priority is multiplication. And now, because we said it was part of multiplication, of course, multiplication includes division. And our lowest level of priority is addition. And again, because it's part of it, that includes subtraction. So up here, to figure out what needs to be done first, do we have any enclosing symbols? No. Exponents? No. Multiplication and division? Yes, so we have to combine the 3 times 5 is 15. The rest of the problem does not change. Each step in an order of operations problem, you're combining 2 numbers to get 1, and the rest of the problem is staying the same. So now we have subtraction and addition. Those both happen on this last level. So which one am I going to do first? You got it. When we have 2 operations that are on the same level of priority, then we do go left to right, just like reading a book. So 9 minus 15 would be first. That's a -6. -6 plus 4 is a -2. So the result there is -2. Let's give you one just a touch more difficult. So 7 plus 3, and then in parentheses 15 minus 6 plus 5 plus 2 times 8 minus 3 times 2 squared plus 1, close parentheses, minus 5 times 2. Just a touch more difficult. Now this looks like a monster, but as long as we follow our levels of priority, we'll be okay. We have more than one parenthesis, more than one enclosing symbol, so we go left to right. Here's the first one we encounter. Where's its other end? All the way down here. So we're going to start inside that set of parentheses, inside the green box, if you will. Now inside that enclosing symbol, order of operations still applies. So we're still looking for more enclosing symbols. We have this parentheses. So now we're going to focus inside there. In there, are there any more enclosing symbols? No. Exponents? No. Multiplication? No. All we have is the addition. 6 plus 5 is 11. Now, once we have reduced an enclosing symbol to a single number, we can get rid of the enclosing symbol. So I'm going to remove the parentheses there as well. Notice the rest of the problem does not change. So now I'm back to working inside this set of parentheses. Any more enclosing symbols? No. Exponents? Yes, 2 squared, which is 4. So again, the rest of that problem does not change. All I do is replace the 2 squared with a 4. What's next? Okay, so inside that box, inside the parentheses yet, I have multiplication and division yet. Or just multiplication, so I'm going to go left to right. So the first one I hit is the 2 times 8 is 16. And then I do have the 3 times 4 is 12. The biggest mistake I see on these is people try to take shortcuts, writing down the rest of the problem. You can see it's taking me a long time to write it down, and it is very tedious. But people try to combine more than one step in there so they don't have to write it down so many times. And that's where I see most of the mistakes being made. So be careful, take the time, and do it out the full way. So now inside there, all that's left is multiplication or addition and subtraction. I'm going to buzz through this a little bit quickly here because I only have like a minute and a half before I lose the network. I haven't reprogrammed it yet. So I'm going left to right. So 15 minus 11 is 4. Four plus 6 is 20. Or 4 plus 16, I should say, is 20. Twenty minus 2 is 8. Eight plus 1 is 9. Now I'm down to a single number, so I can get rid of the parentheses. However, I have this 3 in front of the parentheses with no symbol there. What's implied? Multiplication. So when I remove the parentheses, I do have to put in that multiplication. And now from here, it's multiplying first, left to right, and then adding and subtracting. That's all that's left. I'll finish that off in just a second, but in case the network goes down, for tomorrow, all you have is homework 1 to do in my math lab. So if the network goes down in the middle, that's your assignment for tomorrow. So I'll finish this. Multiplication, left to right. Multiplication and division, I should say. 3 times 9 is 27. 5 times 2 is 10. 7 plus 27 is 34. Minus 10 is 24. The single biggest mistake I'll see students make on this problem, by the way, comes before they even really get started. They'll look and say, oh, 7 plus 3 is 10. Why can't I do that? Because 10, yeah, the 3 here has 2 operations happening. It has addition here, but it also has multiplication after it. That multiplication has a higher level of priority. That multiplication must happen before we can do the addition. So don't do that. Okay? This multiplication. If there's a number next to a parentheses with no operation, that's assumed to be multiplication. Okay. Now there are other enclosing symbols. We won't have time to finish this problem, but I'll put it up here. Like something like this. This line here, most of us know that it means division, but it's also an enclosing symbol. It's telling us to do everything on top first. So 2 times 3 is 6, and 7 plus 6 is 13. Then do everything on bottom. 6 minus 2 is 4. 5 minus 4 is 1. And then divide. So that is a form of enclosing symbol. Okay, I actually went a minute past our time. So we'll lose the network here really soon. But again, homework 1 is your assignment for tomorrow. At the beginning of class tomorrow, there will be time to answer questions on that homework. So make sure if there's a question giving you problems, you write it down. You had a question on can you print the homework off? So let me get to that here. Hopefully, if anybody at the other sites want to see this, the network will hold for us. If not, it'll be at the end of the recording for you. But anyway, as you get into my math lab, in the homework assignments, these should be printable if they copied over from last summer correctly. Yeah, right up here you can just click on print. It should give you options. You may have to open, if that might just print this page, you may have to open a question. And from that, once you open a question, then hit the print up here somewhere, wherever it went. It might be there. Where did it go now? With the new, there it is, print. But at the very least, you can print it question by question. But now, if you're thinking about just working them out before you enter them in, you can see you do have multiple chances to enter them, so you may not need to print them out, especially this first assignment. There's not.
Yeah, I was just thinking more like on some of like the last one is something that to print it out, to work it out before asking.
Yeah, especially later in the semester when we get into geometry, it'd be nice to have that figure in front of you so you can draw on it and write on it to figure out areas and stuff. Okay, we will see you guys tomorrow. I will be here until noon. What I'm going to do is I'm actually going to go down to the network and I'm going to tell them to have the network come up at 8:40 and go down at noon. So those of you at the far sites, you'll have time to access me for that 20 minutes before and 20 minutes after class. For those of you here at Rice Lake, what will happen is if you want to come, I'm usually here around 8:20, 8:25. So if you want to come in and ask questions, you can. At 8:40, when the network comes up, I'll still answer your questions. But if somebody on the network has a question, I've got to defer to them because they don't have access outside the network.
So will this video be on Blackboard?
This video should be on Blackboard within an hour. It takes about 30 minutes to process a video that long, so it'll take a while to get it up there.
Well, thank you very much, sir.
You bet. Have a good one.
Thank you.